Hello and welcome. In this video, we're going to talk about using differential equations to solve growth and decay problems, and we're going to focus on the basic law of exponential growth and Newton's law of cooling. Let's go ahead and jump right in. You first learn about exponential growth and decay in Algebra 1 and Algebra 2, where you're given a variety of formulas, half-life formula, compound interest, and you're applying those to a given situation. But those formulas actually stem from calculus. When the rate of change of a population is proportional to the amount of that population, we can actually model it with this differential equation. dy dt is equal to k times y. So the rate of change of y with respect to time is equal to some constant of proportionality, some ratio, times the amount of the population or whatever we are talking about. If we solve this differential equation, we're actually going to come up with a formula that you have used in previous classes. So let's go ahead and set this up so we can solve it using the separation of variables. So the first thing we would want to do here is get y on the same side as y's and dt on the other side. And since k is a constant, we can integrate that with respect to t. So over here, we're going to get natural log of the absolute value of y. And here we're going to get k times t because k is just holding the place of some number. And now to isolate y, we're going to exponentiate both sides. So e to the power of this and e to the power of that. I'm going to come up here. That's going to give me the absolute value of y is equal to e to the power of kt plus some constant. And then I'm going to bring that constant down, and I'm going to drop the absolute value because by changing that constant, we're going to deal with any potential positive, negative sign issues that we would have. So here we have the basic law of exponential growth and decay. You might have seen something similar in previous classes, something called continuously compounded interest. Same basic formula, just uses different variables. So let's dig into this a little deeper. In the formula for the basic law of exponential growth and decay, we have a few things going on. We have our C value, which is just the initial value. C is what we could find if we're given an initial condition to plug in. We have our K value, which is the constant of proportionality. Both of these values are just some number. So once you find them once, they stay in your general model for the problem. The things that are changing are time, and then based on that time, the amount of whatever object we have. So what we're going to do in the rest of this lesson is we're going to focus on using this formula, the basic law of exponential growth and decay. All right, here we go. The rate of change of y is proportional to y. What that means is we get to use this y equals ce to the kt model. Find the indicated value. So if t is equal to 0, that means that y is equal to 2. That's like using the point 0, 2. If we plug in the point 0, 2, that's going to give us c times e to the power of 0. E to the power of 0 is 1. So c is 2. And you don't really need to show this work if you're given an initial condition like this with this model. So let's go ahead and rewrite that with our c value plugged in. We still don't know what k is, and k is the only other value that's going to be constant no matter what, so we're going to use this second piece of information to find k. If I plug 4 in, I get 2 times e to the 2k. Remember, we're plugging in 2 for t. We can divide both sides by 2. To solve for k, or to get k out of the exponent, we're going to natural log both sides. Natural log of e is 1. So if we solve this, we're going to get that k is equal to natural log of 2 divided by 2, or 1/2 natural log of 2. And then we can plug this value back in to our model. So y equals 2 times e to the 1/2 natural log of 2 times t. The question is asking us specifically, what's the value of y when t is equal to 3? So we're going to go ahead and plug in 3 of natural log of 2 times 3. And then if you didn't have a calculator, you would just leave your final answer like this. If you did have a calculator, you could plug it in to find that specific value. Let's go ahead and look at another problem. All right, here we go. What is the rate of growth? Rate of growth is referring to k. So our ultimate goal in this problem is going to be to find k. of a population whose population triples 3 times that population every 100 years. So here we know that originally we have some population C, and over some amount of time it's going to triple and become 3C. We know this happens when T is equal to 100. So if we're using the model y equals CE to the KT, we can plug in that we know that 3 times happens, so 3C happens when T is equal to 100. And then it actually doesn't matter here that we don't know the initial population, because we can divide both sides by C, and then we can natural log both sides. And then we can find our K value, 1 over 100 times natural log of 3. And again, you can use a calculator to find that value, and if you don't have one, you could leave it like this, or maybe write it like natural log of 3 over 100. Let's look at one more example of the basic law of exponential growth and decay, and then we're going to move into Newton's law of cooling. So I'm going to encourage you to pause the video, try this problem on your own, and then unpause the video and see how you did. If you get stuck, unpause, and I'll give a couple clues along the way. So here's my first set of hints. We're given that C value, since we know the initial amount of bacteria. We're given information about 2 days later, and we're given information about what we're looking for. So go ahead and set up the model, then use that blue ordered pair to see if you can find the K value if you haven't already done so. So here's the work for finding K. Then we can plug in K and T equals 5 to our new model to find the solution. Here's that answer, and then I believe if you plug this into a calculator, you're going to get that there are 551.135, or approximately 551 bacteria present after 5 days. All right, the last thing we're going to talk about is Newton's law of cooling, which is just a modified variation on the basic law of exponential growth and decay. And in this model, we keep in mind the actual temperature of the room that we are looking at, and that is the T sub S. So what we're saying is we may have a directly proportional difference, but the room temperature is also going to play a component or play a part in determining how long it takes to cool an object. So you can see the differential equation version over here on the left, and you can see the exponential version over here on the right. And what we're going to do now is we're just going to apply this formula to a couple of examples. All right, a hot pocket is removed from the microwave with a core temperature of 398 degrees Fahrenheit in a room that is at a constant 68 degrees Fahrenheit. After 5 minutes, you take a bite and you burn your mouth because the hot pocket is still 242 degrees. How long will it take for the hot pocket to be ready to eat at 155 degrees? So let's go ahead and write down the model. And then we can plug in that we know the room temperature T sub S is 68 degrees, and we can use 398 to find our C value. So if we plug in T sub S and the initial condition, we can find that C is going to be 330 degrees. And then we can rewrite our model and use the point 5 minutes later, 242 degrees to find our K value. So go ahead and pause the video and do that. So after we plug in that 0.5, 242, we can isolate the E term, and then we can natural log both sides to find that K is going to be 1/5 times the natural log of 29 over 55. And then we can plug this information in and set Y equal to 155 to solve for T. So we're going to find T. So here's the setup for that. And then you can go ahead and pause the video and work through the solving. You can either use a calculator to find the decimal answer, or you can leave your answer in terms of natural log. And here is the solution. And then we would write our final answer in a sentence. It will take approximately 10.414 minutes for the hot pocket to reach 155 degrees Fahrenheit. Let's do one more example. For this last example, I'm going to encourage you to pause the video and to work through as much as you can on your own, and then unpause the video and I'll do short pieces at a time. So since we're given information about the room temperature. We know we're going to be using Newton's law of cooling, and we can plug in 60 for T sub S. We're given that it cools from 100 degrees. So it started at 100 degrees to 90 degrees in 10 minutes. So that's going to give us two ordered pairs. We can use the 0, 100 to find C, and then we can use the 10, 90 to find K. So there's the work for finding C and the setup for finding K. And here's the value of K. The last part of this question is asking us how much longer will it take for the object to reach 80 degrees. So we're looking for when T, what value of T makes the output 80. Go ahead and set that part up. When you solve for T, you're going to get 24.094. So after 24 minutes, it's reaching 80 degrees. However, the question is asking us how much longer, which means if we already went 10 minutes, we're going to subtract 10 from this answer to get 14.094 minutes. It will take 14.094 more minutes for the object to reach 80 degrees Fahrenheit. Let's go ahead and wrap up this video. All right, wrapping up this video, we talked about the models for exponential growth and decay, and we specifically noted the basic law of exponential growth and Newton's law of cooling. We looked at word problems in context and how to use these formulas to determine an indicated value. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.